All right, so for this example, it says that a 6.2 kilogram object has a force of tension of 30 newtons that's pulling with it. It also has a force of friction. So there's a few things that we need to know. Number one, what is the force of the net force in the y direction, what's the net force in the x direction, and what's the total acceleration of the system? Well, first off, with the net force in the y direction, there's no acceleration in the y direction, so that means there's going to be no net force in the y direction. All right, if you think of Newton's second law, net force equals mass times acceleration, so with no acceleration, you have no net force. All right, now looking at the x direction, the net force in the x direction, well, we got forces that are acting in the x direction. I don't know if it's accelerating or not, but if you look at the force of tension and the force of friction, you can see that they're not the same. So there's going to be some unequal amount of force. So we start with our free body diagram. Our free body diagram has all the forces that are acting on our system. You can see that we have a normal force that's going to be upward, force of gravity downward, force of tension forward, force of friction backwards. All right, so in looking at the x direction, we're looking specifically just at the horizontal direction, just the horizontal. So when we add these forces together, we have to include the direction that they're moving. You got force of tension forward, force of friction backwards. So the net force is going to be equal to the forward force of tension minus the force of friction backwards. So we go ahead and take 30 minus 50, and we get a total of negative 20 newtons for our net force in the x direction. Now to find the acceleration, since we do have a net force in the x direction, that means we're going to have an acceleration in the x direction. So we use Newton's second law, net force equals mass times acceleration. So we use that net force of negative 20, the mass, which is going to be given in the problem to be 6.2 kilograms, and then we plug that into our equation, divided by 6.2, we get an acceleration that's equal to negative 3.23 meters per second squared for our system. In this example, we have a crate that is being pulled upward with a force of tension of 58 newtons, and then the mass itself is 25 kilograms. So to determine the normal force, we first need to start with our free body diagram. We've got the forces that are acting on this system. If you think about it, we got the force of tension that's going to be upward. We got a force of gravity because it has a mass, but we also have this surface here of normal force, and that's going to be applied upward also. So we got our tension upward, our normal force upward, and our force of gravity downward. To determine the normal force, I got to use Newton's second law. Net force equals mass times acceleration. So we're looking specifically in the y direction. The y direction is going to be the normal force of tension. Notice that these two are going to be upward, so they're going to be positive. And then we have a force of gravity downward, so that's going to be negative. Now the net force is going to be equal to 0, and the reason I know it's 0 is because it's going to be sitting here, not going anywhere, and not accelerating, not moving. So the normal force upward minus the force of plus the force of tension minus the force of gravity is going to be equal to 0. We take the normal force, or the force of tension that's given to us, that's going to be 58 newtons, minus the force of gravity. We have an equation for force of gravity, which is mass, that's 25 kilograms times 9.8. We go ahead and plug that in. The reason it's a positive 9.8 is because the negative is already right here, so we don't put it in twice. So we get 25 times 9.8, that gives us 245. So 58 minus 245 gives me negative 187. We take that negative 187 to the other side, we get the normal force is going to be equal to 187 newtons. In our next example, it says, well, what if we remove the floor? What will the acceleration be? So we start with our free body diagram. We have a little bit of a difference here. We do have a force of tension still. That force of tension is upward, but then we have our force of gravity downward, but we do not have a normal force. So in starting with our free body diagram, this time we only have the force of tension up and the force of gravity down. So our net force is going to be equal to mass times acceleration. The only forces we have is a force of tension, force of gravity. The force of gravity is going to be equal to the mass, which is 25 times 9.8. Now this time we do have an acceleration because the force of gravity is going to end up being 245 newtons, but the tension is going to be only 58 newtons, so it's not going to be able to balance it out. So we get the mass times acceleration on this side, plug in 25. We go ahead and solve this side of the equation. It's 58 minus 25 times 9.8. Now what you notice on the previous example, the normal force was 187 newtons, so it makes sense that the net force here is going to be negative 187 newtons since there's no normal force to balance that out. We go ahead and divide by our 25, and negative 187 divided by 25 gives us negative 7.48 meters per second squared. So it's going to be accelerating downward at 7.48 meters per second squared. In this problem, we have several masses that are all attached together, and then we got a force on the front that is going to be 30 newtons that's pulling on it. All right, so the question here is going to be, what is the acceleration of the entire system? What's the force of tension between mass 1 and mass 2? What's the force of tension between mass 2 and mass 3? So to figure out the acceleration of the entire system, we first have to, in using Newton's second law, we've got to define what our system is. In order to use Newton's second law, I've got to do my free body diagram, so I got to first determine what forces are being applied to my system. So my free body diagram, what forces are acting on it? Well, if I look at my system itself, I'll see that there's only one contact force, and that's the force forward of 30 newtons. Now you see the force of tension 1, force of tension 2, and you're like, well, why don't I include those on my free body diagram? The reason is because they're internal forces. Internal forces you do not include on your free body diagram. Newton's third law says mass 1 pulls on mass 2, but mass 2 pulls back on mass 1 with equal and opposite force. So technically, if I want to include force of tension 1 of mass 1 on mass 2, I would have to include the equal and opposite force of mass 2 back on mass 1. Now, since I know those are equal and opposite, they're going to cancel each other out. That's why we don't need to include internal forces. That's one of the powers of Newton's second law, is when we define our system, we have a force inside of our system, we don't have to include it in the free body diagram. So the only force that's acting on our system is that force of 30 newtons forward. So when we go to Newton's second law, net force is going to be equal to mass times acceleration. The only force forward is that force 1. The mass of the system is everything that's in there. So it's mass 1, mass 2, and mass 3 all together. So that 30 newtons is going to be equal to that 5 plus 3 plus 2. That gives me a total of 10. So we divide both sides by 10. We get an acceleration that's going to be equal to 3.0 meters per second squared. In the next problem, we're going to be looking at the force of tension of the first one between mass 1 and mass 2. All right, so let's define our system. If we define the entire thing as our system, force of tension 1 was inside of our system, and we couldn't include it in our free body diagram. So we need to redefine our system so that now that force of tension 1 is outside, is an outside force. So the way we do that is we say that mass 1 is going to be our system. If mass 1 is our system, we draw our free body diagram, and the only force that's acting on mass 1 is force of tension 1. Now you may look at this force out here and say, well, this force is pulling all of them, so why don't we include that on our free body diagram? Well, the reason is this force out here, this force of tension, it's a contact force. We only include contact forces on our free body diagram if that force is in direct contact with our system, and this force is not in direct contact with our system. And actually this force may be pulling on the front one, but force of tension 1, that's what's pulling on mass 1. So we only have that force of tension 1 on our free body diagram. All right, so Newton's second law, net force equals mass times acceleration. I've got this one force forward of force of tension 1, and that's going to be equal to the mass of our system. Now this time our system is only mass 1, so that's all we put over here for our mass. The force of tension is going to be equal to the mass times acceleration. We already have the acceleration over here, so we can plug that in. 5 times 3, that gives us 15 newtons for force of tension 1. Now, something interesting about this that you should recognize is that 5 kilograms is half of the total mass. This is 3 and 2, that's a total of 10. 5 kilograms is half the total mass. Well, all of them are accelerating at the same rate. So if you look at Newton's second law, if I only have half the mass, then that means I should only have half the force in order to accelerate it. So it makes sense that the force of tension on the first one is 15 newtons because that's only half of the total force acting on the system. So for our next one, we need to figure out the force of tension 2. Force of tension 2, and in order to do that, I had to make force of tension 2 outside my system. So I'm going to define my system as mass 1 and mass 2 together. Now that makes force of tension 1 inside of our system, so that's not included on our free body diagram. And this force over here, that's 30 newtons, that's outside. It's not in direct contact with our system, so that is not included on our free body diagram. So the only force that's on our free body diagram is this force of tension 2, because that's the only force in contact with our system, and it's not an internal force. All right, so net force equals mass times acceleration. The force of tension 2 is going to be the only force. That equals the mass of our system. Now we got mass 1 and mass 2 inside of our system, so that's included over here for the total mass of the system. The force of tension is what we're looking for. That's going to be equal to 5 plus 3, so that's the total mass, mass 1 and mass 2, times the acceleration, which is 3. So 5 plus 3 is 8. 8 times 3 gives me 24 newtons. And again, if you think about it, 8 kilograms, that these two together is 8 kilograms. That's 80% of the total mass of the system. So 80%, zero point 0.8 times 30, that gives you 24 newtons. So let's say, for example, that we don't really like the system that we chose before. We chose mass 1 and mass 2 as our system, but let's say, you know what, I don't want that. I want to choose just mass 2 as my system. Well, you can do that. We just have to redefine our free body diagram. Our free body diagram, as you notice, we have force of tension 2 that's pulling forward, but we also have force of tension 1. Mass 1 is pulling on mass 2, and it's pulling in the backwards direction. So our free body diagram is going to include force of tension 1 and force of tension 2. And that force of tension 1 is going to be to the left, force of tension 2 is to the right. So when we go to our Newton's second law, net force equals mass times acceleration, we have to include both of these forces. Now you notice force of tension 1 is positive because it's to the right. We have to make force of tension 2 negative because it's to the left. And our system only includes the second mass, so that's what's going to be over here. Now, force of tension 1, we already know what that is. That's 15 newtons. And technically, we know by the previous slide that force of tension 2 is 24, but let's assume we don't know that right now. So force of tension 1, 15, the mass is going to be 3 kilograms, and the acceleration is 3. So we take 3 times 3, and we get 9. We go ahead and take this negative 15 to the other side, and it becomes positive. 9 plus 15 gives me 24 newtons. Now, the purpose of this slide is to show you that if I define my system as both of these masses, then I get a force of tension 2 that's equal to 24 newtons. But if I only include the second mass as my system, I still get the same force of tension, which should make sense because the only way you're going to get the consistency is if you reuse Newton's second law, but you show the two forces that are acting on it along with the mass of the system.